Section 6.4 talks about the central limit theorem. Central limit theorem is probably one of the most important theorems that we are going to be using throughout this course. Given the random variable x has a distribution with a mean and a standard deviation. The distribution may be normal or may not be normal. It doesn't matter. The simple random sample of size n are selected from a population. So you pick a certain population, a certain group or sample from this population. The distribution of the sample mean. So this sample that you picked, the distribution of the average of that sample will approach a normal distribution as the sample size increase, even if the original population is not normal. If the original population is normal, any sample of that will be normal. Done deal. Normal means I could use the z-score or the z-table. However, if I pick a sample from a population that's not normal, as long as I take the sample size to be large enough, I could assume it is normally distributed. The mean of all the sample means is the population mean. So we assume that the average of the sample that we picked is the same as the average of the population. That doesn't change. However, the standard deviation of all the sample means is going to be the population standard deviation divided by the square root of n. There is an online distribution look at, and that would pretty much go over this if you want to see some more, but here's everything that you need. Note about the distribution. If the original distribution is normally distributed, then any sample of size n will be normally distributed. No harm there. However, if the original population is not normally distributed, then for samples of size n bigger than or equal to 30, if you pick 30 or more from this population, we assume the distribution of the sample mean, as long as you amend the standard deviation, we assume that those are approximately normally distributed. So here's an example. Find the sample mean and the sample standard deviation for the given distribution. Given a normal distribution with a mean of 10, the mean of the sample distribution is 10. And the standard deviation of the means would be 3, which is the standard deviation. You know what? I should write that in notation first. So that is the same as the population, which is 10. This is the population standard deviation divided by square root of n. That is 3 divided by 3, which is a 1. So here we have a population that is normal, given the mean and the standard deviation. Then what we get a normal distribution with the mean of x bar, which is our sample mean, and this is still normal. Not a big deal, because any sample of a normal distribution is normal. What if I was looking at a general distribution like this? Given a distribution with an average of 77, standard deviation of 14, n equal 49, I will say the average of the means would be the population average, which is 77. Nothing to do there. But the standard deviation of the means will be the population standard deviation divided by the square root of n. That is 14 divided by the square root of 49. That is 14 over 7, which is 2. Notice that n is 49, which is bigger than 30. This is definitely not normal. We're given the mean and the standard deviation. We're going to assume that the sample that we picked, the sample of 49, there is the average of the means, population standard deviation. We're going to assume that this is normal, which means Z can be used. So that's the only condition that we have. So steps to use sample distribution for the means. Check if the mean is normal, or if it's bigger than or equal to 30. Find this, you set equal to the population. This, you take the population mean divided square root of n, and use the normal distribution, and the rest is identical to what we did before. Now, we're going to look at some examples, and let me demonstrate really quick how this works. So anytime you see a normal distribution, you should know that we could use the Z table, and the Z table meaning our TI. So here we go. It says the GPAs of all students enlarged in a large university, normally a large university have a lot of students, has a normal distribution with a mean of 3.02 and a standard deviation of 29. Find the probability that one randomly selected student will have a GPA greater than 3.2. So this university, they have a mean of 3.02 for their GPA with a standard deviation of 0.29. So if the mean is 3.02, isn't 3.2 to the right of that? Somewhere to the right. Again, this is not to scale. So when you say find the probability that a randomly selected student, one randomly selected student, will have a GPA that is greater than 3.20, isn't that to the right? And there it is. I'll get my calculator out. I already opened that for us. And I'm going to go for distribution. I want normal CDF, if you recall how this works. And I'm going to go from 3.2 to the upper 1, if you remember, e to the 99, that's like to infinity. What's the average? The average here is 3.02 because that's x, that's not z. And the standard deviation is 0.29. And tell me what that probability, and I'm done. And there it is. So if I know it's normally distributed, or the population is normal, I could always do this. And if the population is not normal, if n is bigger than or equal to 30, then guess what? So we have a 26.74% chance of that happening. So if the population is not normal and n is bigger than or equal to 30, guess what? I could use normally distributed. How about here? Find the probability that, so this is for one student. Find the probability that 25 randomly selected students will have a mean GPA greater than 3.20. That's all 25 of them. Well, here I have to make an amendment that I'm going to assume the average is still 3.02. However, the standard deviation, since I'm looking for the mean GPA of the 30, I'm going to take this to be the population standard deviation divided by the square root of n, which is 25. And this will be 0.29 divided by the square root of 25. And that would be 0.29 divided by square root of 25 is 5, by the way. 0.058. 0.058. So here I am. Now I'm looking for a probability that the mean of those 25 is greater than 3.20. Unlike this is an individual student, this is the 25 students. That's going to be, this is still 3.02. and this is still 3.20, and I'm still looking to the right. My calculator already has that information. Oops, I clicked the wrong key. So I'm going to go for the normal. Everything's still there. The only difference, I'm going to change the 0.058 if I'm not mistaken. 0.058, that's right. Let me just make that a bit more clear. So oh crap, I put it on the stack to graph. I'll clean that later. Here, I'll clean it now. Okay, quit, and if I go back again, so now everything's in place, and there it is. And if I figure out what this is, the chances that all 25 of them, their average, the average of the 25 being bigger than 3.2. So for one student, we found that to be, there's 26.7% chance of that happening. Here we figured out that this is 0.009566466. So that's roughly 0.1, not 1%, 0.1%. Look how much that changed, because that's 25 of them. That's a lot more. It's harder for the 25 than just an individual student. And how about now, part C, find the probability that 10 randomly selected students will have a GPA between 2.9, so remember this is 3.02, 2.9 is to the left, and 3.10 is to the right. So I'm looking for this area. Well, find the probability that n equal 10 in this case. Those 10 will have a mean that is between 2.90 and 3.10. Well, here the average is still 3.02, and even though this is, I'll point that out in a minute, it was what was it? It was 0.29 divided by radical 10, and if I take 0.29 divided by radical 10, 0.0917, 0.0917. All right. So even though n is 10, well, here I don't have to worry much because they told me that the population is normally distributed. Otherwise, I wouldn't be able to do this because n is not bigger than or equal to 30. Well, this is simply, again, the use of a calculator. I'm going to go to my distribution. I want normal CDF. And I'm looking, the lower end is 2.9. The upper end is 3.10. That's the same, but this changed. Right now, it is 0.019917. 917. And there it is. It's always easier to be in an interval than to hit a specific number. So there's a 71.32% chance of their average mean be between those values. So the answer is 71.32% chance of this event happening. Alright, how about here? Let X equal CEO salaries in thousands, where X is skewed to the right. Obviously, CEOs make a lot more than the average people, with a mean of 139,000 and a standard deviation of 45,000. If all possible random samples of 40 CEO salaries or in thousands are taken, how would you describe the distribution of the sample means? What would the standard deviation be? Well, I will describe this to be normally distributed with an average of 139,000, and the standard deviation would be the population standard deviation divided by the square root of 40, which is 45 divided by the square root of 40, 7.115. And why is that? They didn't say the population was normal because n equal 40. Here they have the mean skewed to the left with 139,000 with 45 for the standard deviation. I'm going to assume that this is the population, which is 139,000, and this is and there it is.